Hello, and welcome to this APIS training introductory course on Docker and Kubernetes. As the title says, we start in this one from scratch for both of these technologies, and I feel like they could have been in separate courses, each one of them, but they are so tightly bound that it would be unfair to do that, and it's the best way to learn both of these technologies is to cover both of them in a single course. My name is Cvitan Gricin. I am a software engineer with over 12 years of experience. My experience has mostly been in software. As a software developer, I've gone through many roles of senior developer, technical architect, team lead. My current role is a DevOps engineer at Keitaro. And you can see my personal mail over there. Feel free to contact me if you need to do so. About this course. So the materials we used for this course are the official documentations for both Docker and Kubernetes. You can find the links over here. And the goals of this course are to learn Docker and Kubernetes, right? Well, at the end of this course, you will know how to build, compose, deploy, and manage Docker containers. You will understand what Kubernetes is, how to run things on Kubernetes, and how to manage your containers on that platform. The prerequisites for this course are the best target audiences for this course are actually DevOps engineers, solution architects, and any software professional. But you don't really need to be in any of these roles. Any enthusiast can follow along since, after all, this is a beginner's course. Now, knowledge of Linux or Unix is very helpful in this course because all the exercises are going to be done in a Linux machine. After all, I'm running a Linux machine myself, but don't worry if you are a Windows or Mac user. The exercises are made in that way that you can follow the exercises easily as well. Now, the course agenda. We have broken down the course into a lot of chapters, and the topics we are going to cover in those chapters are, first of all, we are going to introduce you to Docker, what it is, what problems it tries to solve, what was the history behind it, and so on. Then we'll move into setting it up on our local machines, so on your laptops. And as I said, fear not if you have Windows or Mac OS. It's not an issue because we are going to be using a virtual machine to do all of our exercise, and you can do that on any operating system that we mentioned. So Linux, Windows, Mac OS, all of you guys are covered. Then we will move into the core of Docker, and we will explain how to manage the containers with a Docker client. This is a huge topic. It's going to be broken down into two segments, and there's a lot that we are covering over there, like networking, how to run containers, how to manage them, and so on and so on. Then we are going to tackle two extra topics. Those are Docker images and Docker volumes. And the last one that we will tackle on the subject of Docker is Docker files. Before we move on to Kubernetes side. And over there, first of all, we are going to do another introduction to Kubernetes, and we are going to do both some basics and advanced operations. And at the end, we're going to cover a bit of the Kubernetes administration. So follow along, and let's start with the introduction. The introduction of Docker. So the agenda in this first chapter is to find out what Docker is, why do people use Docker, what's the history behind it, what are the issues that it tries to solve, why was it invented in the first place, right? So in this chapter as well, we're going to learn what containers are. Everybody's talking about containers, but we're going to tackle exactly what containers are and how Docker is managing containers. And along the way, we are also going to find out what the historical advancements have been in this area, like physical servers, virtual machines, and then containers. We're going to see why all of that transition happened. And at the end, there's something that usually is not talked about a lot, but we also have images. Everybody talks about containers. Not a lot of people mention images, and they are an integral part of what Docker does as well. Let's start. So what is Docker? I have pointed out here two definitions. The first one is the official one from the Docker portal, which is docker.com. And it's kind of a marketing thing here. Like it says, with Docker, you could securely build, share, and run modern applications anywhere, right? Doesn't explain much, but it's a marketing term. The second one is from Wikipedia, and it's a bit better in order for us to understand what Docker is, in my point of view. So it's a bit longer. I'm going to read it. Docker is a set of platform as a service products that use operating system level virtualization to deliver software in packages called containers. So let's break this down. Let's break down this sentence. So it is using some kind of virtualization. So it is using some kind of virtualization in order for you to be able to run some applications, right? So that's similar to virtual machines, right? But there's a big difference, and that difference is shown over here. These are my own two breakdowns of what Docker is. So first of all, for me personally, Docker is a package of three things: operating system, libraries and dependencies, and the application itself. So with virtual machines, you would have your application running on a virtual machine. But the operating system and libraries are there in the virtual machine itself, and you cannot really mix and match. We're going to tackle this in the next slides. So just remember, a container is a package that contains all of these things for you. So when you ship the container, right, we're going to be using a bit of normal terms, right, from the shipping industry. So you ship containers on boats. With Docker, it's the same thing. You ship containers. But those containers contain everything you need for your application to run. So another thing that I want to tackle here, in order for you to understand what Docker is better, is that those same containers can be running everywhere on all of your environments. So you have the developers, the testers, the staging environment, the production environment, and you can have anything in between those. So in each of those environments, you run the same exact container. We're going to tackle this in a moment. First, let's do a bit of history. The original inventor was Solomon Hykes. He created the Docker company back in 2011 with another guy, but he is the inventor of Docker. And he started the Docker project in 2013 as an internal product in a company called .cloud somewhere in France. They worked on it for some time, and in March 2013, it was publicly shown during a PyCon conference, and it was quickly open sourced as well in the same month. So the first glimpse of what the public could see about Docker was back in 2013. Things started moving on quickly after that, so a lot of big name companies started noticing this technology, and right around September, so 6 months after it went open source, Red Hat decided that it's going to collaborate with Docker and integrate it with its products, namely Fedora, Red Hat Enterprise Linux, and OpenShift. This was a huge step for the project, and it kind of picked on after that. A lot of other companies joined, like Microsoft, Google, Cisco, and others. I'm not going to mention all of them. To put it simply, it was an explosion in adoption. But I feel like the best usage came and adoption came right around 2015, maybe 2016, and that's exactly when I had my first taste of Docker, somewhere in the mid of 2016. The current version, so what's the latest thing? So there's a lot of things happening between. I'm not going to tackle all of it. The latest version right now is 19 something. So a lot of versions, a lot of new features, and it's still growing. Now, as I said, it was invented somewhere in 2013, right? So why? Why was it invented? To have a glimpse of that, of the answer for that question, we need to see what's been historically out there. How do we did things before containers, right? So the first thing that happened right around the start of the modern IT industry was around in the 60s and 70s, and back then up until the late 90s and beginning of the century, we had physical servers. In the beginning, those were mainframes. Then later on, we moved to rack operated servers and so on and so on. But still, we used physical servers to do everything. What do I mean by that? So imagine you have an application and you need to run it on a machine. You need to provide a physical machine for your application. And on that machine, you need to install one OS and only one. And then you need to install all your libraries and pre-required tools so that your one application can run. In some cases, you could be able to run more than one application on a single physical server in this manner, but usually what people did was one application per one server. So one OS, one set of libraries, one application for each server. If you wanted to run a second application, you just simply provide another physical server, right? And in this manner, the isolation between those applications was done on a physical level. It was very good isolation, but it was very costly. Why? Because you need to provide a new server for each of your applications, right? And this was something that wasn't really thought about much in the old days, but what about scaling? Today everything is about scaling. Well, if you wanted to scale your application, you just move it to a better server with higher specs, with more RAM, with better processors and so on. And that was a costly operation as well. So you need to buy new servers and you need to move your applications to that new server. It was very time-consuming and costly operation. So to put it simply, the management and portability were very, very low and very, very costly. So somewhere around the end of the 90s, beginning of the century, something happened. People said, okay, this isn't going to cut it, right? So we need to do something about this. Applications are growing in size, we need to do scalability, and so on and so on. The internet started to boom, and suddenly you have the need to scale your applications and to do it faster than traditionally. You don't want to wait for somebody to provide a new server. So go to the store, buy it, ship it to your office, your data center, install an operating system on it, and so on and so on. You want to do this faster, right? So virtual machines were invented. And now you could also run more than one virtual machines on a single machine, right? And the utilization skyrocketed, right? So before, you have your one application, it could be sitting there and doing nothing for most of the time, but your server is there and using power and network and all those resources, right? So now you could plan your data center and your servers, your physical machines, so that they could run more than one virtual machine at a time, right? And the isolation level was no longer at the physical level, but it was somewhere in the operating system. So let's see what happens then. You still have one OS per virtual machine. Sorry, these are the physical servers. So let's go to the virtualization. So you have one operating system for your host, for your physical machine, or just a hypervisor. But then you could serve multiple virtual machines, and each one of them can have their own operating system. You see, so you can mix and match now. You no longer need to have a single operating system for your applications. You just run a new virtual machine with another operating system or with another set of libraries that you need for your application to run, right? And so this way we can utilize our servers better, right? They no longer need to sit at 5% of CPU time, right? And there are overheads, like the biggest overhead is the disk usage. So that's the con in virtualizations. So you can share your CPU and memory between virtual machines, but your disks are there. You cannot speed them up. All of your virtual machines are trying to write to those disks at the same time, and this is where the performance might suffer. So you still need to balance things out according to your requirements of your applications to write on a disk. And we have a slightly better management and portability. So there are options and methods of taking a virtual machine and moving it over to another server. That's okay, but it still didn't feel right. It was enough at the time, but it was still costly. Not so costly as with the physical servers, because you could move your virtual machine to another server that is less utilized. You might already have that machine in your data center, but it's still huge virtual machines, huge images that you need to move. And the isolation this time is a bit more affordable. Somewhere 10 or 15 years ago, this moved even one step ahead, and we started seeing clouds and virtual providers like Amazon, AWS solutions, and then Google Cloud and Microsoft Azure, and so on and so on. And they sped up a lot of the manual work that we needed to do with those virtual machines. They even have health recovery and so on and so on. But all of these operations depend on the speed at which your virtual machine can reboot or run. So it's not costly in terms of time spent on human labor, but it's still time consuming to do, because virtual machines don't just fire up like that. You know, they still need to boot the operating system that they're using, and so on and so on. And this operating system is quite a bit of overhead. So you have the operating system on your machine or the hypervisor, which is a lot less resource consuming, but you still have an operating system in each of your virtual machines. Very big overhead. So what did people do? They said, okay, this is not going to cut it. We need to do something even more lightweight, even more portable, even more affordable. The solution was called containers. Now, containers provide the cheapest isolation. They're lightweight, portable. You can read all of those points over there, but let me give you a real scenario. So you have a container. It has its own operating system. It has your required libraries. It has your application. But that operating system is not really there. It's just mimicking one. It's actually using the operating system from the physical server, or the hypervisor from the physical server. So you no longer have an overhead of having an operating system in each one of your containers. And that's why containers now can run in seconds instead of minutes, which was the case in the virtual machines. So almost no performance hit, no duplication of operating systems, smaller attack surface, because you really do not have that operating system there. It's just a mask. We're going to see how that is achieved. And when this technology matured a bit, so now people said, okay, now it's even more easier to do what the cloud providers did for virtual machines, and that's continuous integration, continuous deployment. So you could build your application and deploy it and run it in seconds. Especially the last part, run it. That's in seconds. Sometimes even milliseconds, depends on your container, how big it is. And the general rule of thumb is that you want to do your container, to create your container to be as lightweight as possible. So have tools and libraries only needed for your application seated and nothing more. Okay. There's a lot of, that was a lot of marketing speak. Let's go and see what happens underneath the hood and why containers are so lightweight and so on. So Docker itself is not a container. Docker is a software that is used to run containers. So the other thing I want to mention is that it uses images. Okay, so we need to differentiate between containers and images. So images are templates or packages that have all of what you need, like the OS, the libraries, and the application. I said that the container is that, but no. I mean, both of them have those things, but the image is what you transport. The container is what is running from that image. So the naming convention is a slightly bit different from the shipping industry, where you ship the containers, you transport them. Over here, you transport images, but then you run them as containers. And as I said, all Docker images are built with all dependencies and environments, variables, and operating system you need for your application. So if we take a look at this diagram, this is how things look on a physical server, right? So you have, so this is the gray box is your physical server. So we have your operating system, your kernel, then you have all of the libraries you need, and then you have one or more apps on it. But as I said, historically, usually only one app was in there. Why? Because these libraries sometimes don't mix and match well. So let's say you have two applications, each one of them needs the same library but a different version of it. This is sometimes a problem and cannot be achieved. So in reality, this is just one up here. And with containers, so again, we have a physical server. That's the gray box. And the only thing that's shared between the containers is the operating system, the kernel. And then you have individual containers running on your machine. And each one of those containers has both the app and the libraries you need. So now if you need Java 8 as a library here, but Java something older, let's say 1.6, you can do that in separate containers on the same machine. Sometimes it's possible to do that thing with Java in a physical server, but there are other technologies out there that cannot do this. For example, Node.js applications, they are notorious for this. You cannot have more than one Node.js active in an operating system. There's a trick to install more of them, but only one of them is active at a time. And if you have one application that relies on one Node.js version and another one that relies on a newer one, for example, that's not possible with a physical server. It is possible with a virtual machine, but as I said, on a virtual machine you have your infrastructure, so this is the physical server, then you have your hypervisor or a fully operating system, and then for each of your machines you have a separate operating system. So that's a big overhead there. You see, so your application might be this tiny slit. So on this diagram, these things are not represented in their real sizes. So this would be a huge one, and this would be something tiny, right? So just to run this tiny thing over here, you need to have this huge operating system that's gobbling up all your resources from your machine. And again, with Docker, so these are official images for the Docker portal. You have your physical server, your host operating system or a hypervisor. Then you have Docker, which is not a big overhead in this case, but you no longer have operating systems in your containers, right? And again, these are not represented in real sizes, so these would be just slight here, and this would be huge over here. That's how big the difference is. So these might be using gigabytes of memory, each one of these, because each operating system requires some memory to run and some percent of the CPU time, but these over here don't have that overhead because you're using the operating system from your physical machine. We are going to tackle how this happens in a moment. Bear with me. This is it. So containers, Docker did not create containers. Containers were there before Docker even appeared. Containers, I mean, the technology for containers was there in the Linux kernel even before Docker was invented. This is highly technical, but the separation and the isolation can be done on the kernel level, and this is just for Linux, at the beginning at least, with these two technologies in the kernel. One of them is namespaces, the other one is kernel C groups. I don't think this course is a good place for me to explain all of this stuff, but just bear in mind that these two technologies in the Linux kernel is how you can achieve isolation between your applications, thinking that it has its own operating system when in reality it's just using the one from the machine. So these two technologies fool our application into thinking that they have their own operating system with all of these resources just for themselves. So you have different processes running on your container, on your OS in the container. You have separate network, you have different users, and you have separate file systems. So everything you need to think that you have the machine just for yourself, while in reality you are sharing it with hundreds, if not thousands, of other containers. A quick overview of what a Docker environment looks like. So this is not really how everything operates, but just a high-level overview of what you are encountering when you're working with Docker. So Docker itself is just a command line tool. It has two components, a host component and a client component. In the client component, you can have a command line tool. So you open a terminal and you just type Docker and you can run it. Or you could use HTTP remote APIs to access the host component of Docker. The host component of Docker is the biggest, the most important one is the daemon. And this is what you are connecting to via your clients, either the terminal tool, the command line tool, or the remote APIs. So you connect to the daemon. The host component also has a software that's responsible for the images you're transporting to and from your machine, and it's responsible for running the containers. The third component of this whole environment is something called Docker registry, and that's a central public place where you can retrieve the images from. There are various different registries out there. The one we are going to use in this course and the one you need to remember most is Docker Hub. Docker Hub is a public online tool or portal for keeping Docker images. This is the URL. And when you install Docker on your machine or anywhere, by default, it is configured to retrieve images or to push images from Docker Hub. And I said public, but there are options to have private registries in there. For example, if you are a company, you don't want to have your images with all your software readily available out there for everybody. You want to secure them, that's available. You have user group management, private repositories, and so on and so on. And Docker Hub as well has quite a good integration with modern tools for continuous integration like GitHub, Bitbucket, GitLab, anything that's out there and that's important and known has an integration with Docker Hub. So I'm going to tackle in the final closing minutes of this chapter, I'm going to tackle a few use cases. First of all is there's a big shift in mentality on how you run servers or virtual machines against containers, right? So with physical servers, what happens is you treat them as pets, right? They're important to you. You don't want them to break down. So you give them names, meaningful names. For example, I remember at my university we had Zeus and Alexander and so on and so on. And that thing replicated in each of the companies I went where we had physical servers. They're important. You are proud if they don't go down, right? So you're proud of their uptime. So anytime you go online and you see some system engineers and they say, this server hasn't been down in 3 years, right? That's important to them. You treat them like your family almost, right? The same thing we do with pets. You get a dog and you treat it like a family. It's important to you. If it's sick, you run and try to solve that issue immediately, right? So it's kind of a bit the same with the virtual machines, but now you have more of them in a single physical server, but you still treat them as pets. Both the host operating systems, both the physical servers and the virtual machines, right? So you need to tackle all issues now with both the physical servers and your virtual machines, and all of them are important, and you copy all of these things for each of the virtual machines that runs, right? So you still want your virtual machines to be up and running and not failing. And it gives us a bit of flexibility. As I said, we can move them, we can stop them, restart them fairly quickly, usually in minutes, sometimes more, it depends on your case. But then when containers came along, this term became popular. Pets against cattle. So when containers came, we started treating them as cattle. I mean, sorry for those animal activists out there, but this is true. What do people mean by treating them as cattle? If a container goes down, you don't rush doctors to heal it. You just let it die. If it doesn't die on its own, you kill it yourself, literally. You just leave it fail and you run a new one, right? And that's how you treat cattle, right? It's just a big herd. So you have a big herd of containers. One of them dies. Okay, we'll just get another one, right? So the other thing to mention here is that most of this work, like leaving it die or killing it yourself, restarting another one, most of that work today is automated, and that is something that we're going to tackle in the Kubernetes chapters, but I'm not going to go ahead a lot. Most of the work we are going to do in the exercises for Docker is going to be manually done, because we want to see what's the core and how things are done. The automation is just using those same mechanisms to automate things. So what happened historically if you have a new version of your software, right? So there's a huge list of steps you need to do in order for you to deploy them on physical servers or virtual machines, right? So you need to find all the servers that run the old version, bring them offline, have a compatibility matrix of the old version and the new version, what libraries were needed for the old version, what libraries were needed for the new one, and so on, remove them, install the new ones, remove the old application or upgrade it to the new one, or install the new one, and so on. And all of this took time, took a lot of effort, and we usually saw what were being called as maintenance windows. So you would do this during the night when nobody is using your system, probably over the weekend too, and so on. The same thing happened with virtual machines. It just got a little bit easier because now you can have all the virtual machines in one place and so on. But with containers, as I said, you don't, even with pushing out new versions of your application, you don't go to the container, log into it, update all your libraries, update your application, do all of this stuff that we did with the servers. Again, you don't care. You kill the old one. Previously, you need to make sure you build a new image with everything running right. But then you kill the old one and you just run a new one with the new version. That's it. And this is a very quick operation. As I said, the switch can be in seconds. You still need to build things. There's still some work in the previous steps. But as I said, continuous integration tools and continuous delivery tools, they integrate very well with Docker, and these things can be automated as well. But that's the happy scenario, right? What if you deploy, you've done everything that your steps said you need to do, and still something doesn't work? What do you do? Well, if you ask the developers, they said it worked on my machine. If you ask the testers, they would say it worked on the testing environment or the staging. But still, your production deployment doesn't work. What do you do? Well, you still need to bring, in the case of physical servers, it's the same operation again. Bring down the servers, try to find them. First, bring down the servers, compare what's different between the production and the staging or the testing or the development environment. Test everything throughoutly and hopefully find the inconsistencies, remove those inconsistencies, test, and go back online. Same thing with virtual machines, sorry. And with containers, this scenario is not possible because, as I said, the same container that you run in your development environment or testing or staging, or the same container is being run in production. The only difference, the only issue that can appear here is a human mistake or something in the automated tools that you didn't configure properly, and you actually deploy a different version that what you want. That's the only scenario, and that's highly rarely, and that's probably going to happen once you're going to fix your tools, and from then on, this scenario will no longer bother you. See how mind-blowing this is? So it's a huge step up from the previous technologies. And the same thing applies to, so far we only talked about how to deploy a new version of your application. So what happens if you find a bug not in your application but on the operating system itself? The same things, you need to find the servers, update the patch, and so on and so on. Same thing with the virtual machines. Containers, again, bring down the old ones, run the new ones. Seconds. That's it. You still need to test beforehand on your testing environment or staging, but the actual deployment to production is in seconds as soon as your testers or QA department has confirmed that everything is okay with the new images and the new containers. Huge step up, huge time saving, huge effort saving. So, this was a nice marketing speak about Docker. In the next chapters, we'll go more into the core of how things work. Just a quick summary of what we learned here. So we learned the main difference between physical servers, virtual machines, and containers. We saw the pros and cons of each one of those technologies. And we saw how Docker fits in the container world. So how Docker is using containers to gain popularity and save everybody time and money. Thank you for following me, and don't forget, we have a test. See you in the second chapter.